So we can continue to compute this equation here, just to simplify that. So this is just diagonal matrix, so it's quite easy to simplify. It turns out that we will have a very simple expression just equal to this. And of course we call the sigma WW is really the distortion of your estimate for x hat, because we have W plus x hat is equal to x, something like. So, and we have the constraint that therefore sigma WW should be less than equal to S theta. That's the original constraint we mentioned, that S theta is something like D1, D2, and theta D1, D2, theta D1, D2. So we can substitute S theta into that, and then we can use the matrix immersion formula again on this guy, and then we get something like this. Now, if we pick mu, now we didn't mention what mu should be, but if we pick mu in such a way, like mu equal to 1 over d1 square root d1 and 1 over square root d2, then this term here will be much simplified. It's just equal to n plus 2 times 1 plus theta. And by the way, we actually have the same kind of expression inside one of the term we want to find, that hy given m1, m2. So that term will be quite a bit simplified also. That's one of the three terms. If you remember, we have three terms here for the mu sum bound. This one. We are still trying to compute this one really. So, and if we pick, okay, as I said, if we pick mu to be this, that is a simplify, and then if we further constrain something, that if we insist that we have a Markov chain that x1 and x2 are conditionally independent given y, then we can show that M will have a particular form like this. And this is, the proof is rather straightforward. Basically, we use a result about conditional independence. So if we have Gaussian random variables, three variables, basically, let's see, we have x1, x2, and y. If we have x1 to be conditionally independent of x2 given y, then we will have the correlation coefficient of x1 y, basically rho x1 y times rho x2 y is equal to rho x1 x2. And so we can compute each of the correlation coefficient and compute correlation coefficient of x1 x2. That is easy, it's just equal to rho, and we just make them to be equal, and this expression will depends on n, then we solve that, eventually we get n equal to this one minus rho squared over rho d1 d2. So let's see. So with those choice, we can continue to simplify this expression here. As earlier, we used this matrix inversion formula, and then we simplify the mu transpose S theta mu plus n as n plus 2 times 1 plus theta, and then we have this term here trying to compute that, and we get something like that. So therefore, the inverse of this eventually is just equal to this. We have a form something like this. So therefore, the covariance of the error estimation error of x tilde will be just equal to this guy, where alpha here is equal to this. Now we still haven't finished computing. Basically, again, our goal is actually this guy here, and not really. Our goal is really compute this one here. But of course, to compute this one, we need to compute its covariance. And what we try to do is bound this covariance if this guy here, that's the covariance of the estimation error of x tilde, the estimate x tilde, that's the estimation of x given y hat, that is actually a subset of this guy, and also is not an optimal estimate. And we are almost done finding this one, and actually I think we are done finding this one. That one is just equal to this. And what we have here is we have this guy is bigger than this guy, or bigger than equal to this guy. But one observation, we can make this bound even tighter, is that we realize that for this guy, this has to be a diagonal matrix, because given y, given y, that's basically what we have earlier. Because in the choice of picking mu and n, we insisted that y is something that given y, that x1 and x2 will be conditionally independent. Actually, sometimes this is kind of known as the common information. It's also used in some other problem. So we can't pick y as the common information of x1 and x2. So because of that, then these terms are actually conditionally independent, right? If we think of x1 and x2, so if we compare, let's say, the covariance, the correlation, compare the correlation between x1 and x2 by and this given y, because these two terms are actually uncorrelated, so therefore it will become this multiple can be expanded into two multiple of two expectation, and of course this is just mean of this guy, therefore it got 0, 0 out, so therefore this is 0. So therefore, this term, diagonal term, should be 0. So because these are actually the diagonal terms here, right? So therefore we have this actually has a form like this as a diagonal, as I mentioned earlier. Now what we have is, again, we have this is less than equal to this, and this form I know, and I also know that this has to be diagonal. So we will use some result like this and other small kind of lemma thing, that if we have two matrices that one is smaller than that, and also one is diagonal, the other has a form like A, C, C, then we can show that A minus C squared is bigger than equal to B1, B2. This will imply this. This is rather straightforward to show if you good at solving inequality problem. So, but let's go through it quickly. So if this one is bigger than equal to this, then we need, so this will be positive definite. So this is positive definite, meaning that the determinant of this has to be bigger than equal to 0, and also the diagonal term has to be bigger than equal to 0. So therefore we have these three equations here. And then from these two equations, we have A is bigger than equal to B1 plus B2 over 2. Now we can use the result of arithmetic mean is bigger than equal to the geometric mean. This is basically arithmetic mean of A minus B1 plus A minus B2 over 2. This is bigger than or equal to A1 minus B1, A2 minus A minus B2 square root. So I can square both sides, therefore I have this here. So this is bigger than or equal to this guy, and of course I have another equation here, therefore that this is bigger than or equal to C squared. And because A is bigger than B1 plus B2 over 2, therefore this thing inside is positive, so therefore we have this square is bigger than this square, and this square inside, this thing inside is positive, therefore like this thing we can just remove the square basically. And therefore we have A minus C is bigger than or equal to B1 plus B2 over 2. Again, we can use the arithmetic mean is bigger than geometry mean again. We have this is bigger than or equal to B1 B2 square root. And then we have A minus C squared is bigger than or equal to B1 B2. Now we have that result, and then we can just try to apply this result. But one thing you remember that this is the diagonal is the same here for this guy, but for this guy the diagonal is different. So the first thing we need to do is scale the diagonal. So we multiply 1 over square d1, 1 minus square d2 on both sides. And after we did that, we have basically now this off diagonal. The diagonal term is the same, so we have the form like AACC as we have earlier, and this B1 B2 here. So we have like A minus C square has the bigger than or equal to B1 times B2, and of course B1 times B2 is the determinant of this matrix here. And actually what we are interested in is really just the determinant of this covariance matrix. So therefore this determinant is actually less than or equal to this minus this square, and then we will get this guy here. So now we are essentially done for the mu-sum bound. We have these three terms that we already find it, so we just plug that in. Okay, anyway, this is just algebra. Then eventually we find the bound is just equal to this. So now we have the mu-sum bound, and also earlier we have computed the collaborative bound. So we have two bounds for the sum rate. So this is the collaborative bound, it's like this, and we have the mu-sum bound is actually like this. So both of them depends on theta. We have this is the theta. So remember that theta is kind of like we trade off the kind of how the two distortion of the x1 and x2 are correlated. So we have basically that the s theta is equal to this one again, d1 d2 theta square root d1 d2 theta square root d1 d2. Of course, like we have a constraint that like the x1 has to have, the maximum distortion for x1 is d1 and maximum distortion for x2 is d2, but how these two things are correlated are kind of like arbitrary for us, so therefore we have a theta. So what we want to pick is we want to pick the theta such that our transmission has maximum efficiency, right? Or like the sum rate will be as the bound will be as small as possible. So because like we need to satisfy both bounds, so therefore like we actually it should be maximized. So for theta, something like that really. So we need to pick like, because we need to satisfy both bounds. So eventually the sum weight has to be bigger than equal to this, and we are interested in, therefore like at this point here basically. And turns out this point is quite easy to find because this is just where the two bounds overlap. And so we can just make the two arguments here inside log to be equal, and then trying to solve theta. And if you solve that, you find that it's like a quadratic equation of theta. And then like that will be two solutions, but one of the solutions has a magnitude is bigger than 1, so it should be eliminated. So only have one solution left. And then if there's many algebras, and then after you find theta, and you can actually, this is the theta, 1 minus theta square at least, then we can plug that back in and eventually get the bound is like this. Okay, so that's all really for the Converse proof of the Gaussian multi-terminal source coding problem with two terminals.